Thank you. Good morning, everyone. So, as Vinicius just said, I'll briefly talk about Floer homology, give an introduction to Floer homology. And as mentioned by Renato yesterday, just a flavor of it, Hamiltonian Floer homology. But before we start, let me just recall some of the things that were said yesterday. So if we have a symplectic manifold M omega, and we have a function, smooth function, defined on the symplectic manifold, we can associate with it a vector field, xh, using this equation. So this is my Hamiltonian vector field. And I can associate with it a flow. So this is the Hamiltonian flow, which I'll denote by phi th. And I'll look into the time one map of this flow. So as mentioned yesterday, this is actually symplectomorphism, so it preserves the symplectic structure. So suppose I have a point x here in my manifold M, and see how it moves along this flow. So it's moving along this flow phi t h, and suppose that after time t equal to 1, it comes back here to this, it reaches again this point x. So this would be phi 1 of hx. So what happens is that we have here a one periodic orbit of this Hamiltonian system. So one periodic orbit of the Hamiltonian system. And it corresponds to, or I can find a one-to-one correspondence between this one periodic orbits and the fixed points of this time one map, which sometimes we call a Hamiltonian diffeomorphism. So there is one-to-one correspondence between the one periodic orbits of the Hamiltonian system and the set of fixed points of this time one map. I'll denote this by the set of fixed points of this map. Okay, so in fact here we'll work with Hamiltonians which depend on time. So actually our Hamiltonians will be defined here on R cross M. If needed, I'll assume that M is compact, okay? And also this time dependence of the Hamiltonian, this Hamiltonian will be one periodic in time. So actually here I'll take R mod Z. So taken, given a Hamiltonian, time-dependent Hamiltonian, I can always reparameterize this Hamiltonian in time in such a way that it becomes one periodic, and there is this bijection between the one periodic orbits of the first one with the second one. So if I want to study the existence of one periodic orbits, I can just assume this Hamiltonian is one periodic in time. Okay? So in fact, this vector field will be, I should have a t here, but I'll drop it in the notation. Things now depend on time. Okay. So let me start with actually an application of Floer homology. Let me just make sure. Which is known as the Arnold Conjecture. And in this conjecture, the claim is that the number of fixed points of a Hamiltonian diffeomorphism, so the time one map of a Hamiltonian flow, or if you wish, the number of one periodic orbits of this Hamiltonian system, is bounded from below by the dimension of the Morse homology of the manifold M. Okay, so so this is the Morse homology of M. So before I go into the Floer homology. I'll tell you a little bit about this Morse homology, not just because it shows up here explicitly, but also because Floer homology is known as a Morse type homology. So the way we construct the Floer homology, at least the idea, is very similar. The steps we take in the construction are very similar to the ones in the Morse homology. Let me just say that at some point I'll need to assume something on this Hamiltonian diffeomorphism. I'll assume it is non-degenerate. So hopefully I'll have time to say something about the proof of this result, and I'll assume that this is non-degenerate. I'll define also what is non-degenerate. So let's first go a little bit into Morse homology of a manifold. Okay. HMK, thank you very much. Yes. Thank you. Could I write bigger? That enough? I'll try. Okay. Okay, so let's start with the Morse homology. Is this okay? Or?
Yeah. Just a
Oh, I see. This is in fact really small. Sorry. Non-degenerate. Okay. So to construct the Morse homology, what we do is take a manifold M. Now I'm not in a symplectic setting. I just have a manifold M. And with a suitable function defined on this manifold, I'll construct a complex using the critical points of this function. And we'll define the differential using the gradient or anti-gradient flow lines defined by this function f. So this is the idea. So let me go into the details. We start with a manifold M, compact. And let's take a function f from M to R, smooth. And if we take a critical point P of this function f, so this is how I'll denote the set of critical points, we can define this bilinear symmetric form. I'll write it explicit. I won't need this, but let me define it anyway. So for each x and y, it just gives me x, y of f at a point P. In fact, for this to be well defined, I would need to take a local extension of y, but this does not depend on the extension, so let me just leave it like this. You should think, you can think of this in coordinates represented by the Hessian matrix of f. And so we say that the critical point P is non-degenerate if this, so this is a bilinear symmetric form. We say that P is non-degenerate if this HF P is non-degenerate, or if you wish, in local coordinates that the Hessian is non-singular, the Hessian at this critical point P. So this is a definition. Okay, then we say, write it here, that f is a Morse function if all critical points, all its critical points, if you want, its critical points are non-degenerate. So Morse function. And what happens is that these Morse functions close to critical points, they have this very normal form, if you want, canonical. This is given by Morse lemma. So given a Morse function, okay, then I have to, that for each critical point P in, so for each critical point of F here is Morse, okay? So P is non-degenerate. For all P critical point, I know there exists a neighborhood of this point P, and there exists diffeomorphism, which I'll call phi, from this neighborhood U to Rn, such that, so here let's assume that P is sent to 0, such that F composed with phi minus 1, so I can find coordinates where F takes this form. So at x1, xn, it is given by the value of the function at the critical point minus, let me write it, x1 squared, etc., minus xy squared plus xi plus, sorry, this is getting really small, xi squared plus xi plus 1 squared plus, etc., plus xn squared. So I have the second degree polynomial, and I have all these minus signs here first, and then the plus signs. So I denote it by I, if you want, this I corresponds to the number of negative signs that appear here. Okay, so let me give an example, or a couple of examples. Move here. First example, let's start with the sphere, actually map we saw yesterday. Let me start with S2. And let's consider the height function here on this manifold. So this is a map from S2 to R. If you want to each x, y, z here, or x1, x2, x3, just to use the same notation here, it maps to x3. Okay? So here I'll have two critical points. This minimum, let me call it an S for south pole, and a maximum, which I'll call N for north pole. Okay? Have these two critical points. So the Morse lemma actually tells me that, so locally, close to N, for instance, this critical point, this F, here equal means I can, phi composed with, F composed with phi minus 1. Okay? This F is equal to F of this critical point N. In this case, we know it's 1, but let me write it like this, minus x1 squared minus x2 squared. And close to the south pole, to the minimum, this F is equal to the image of S by this map F plus x1 squared plus x2 squared. So locally, F is given by these expressions. Second example, so this was S2. Let me consider the torus here. And let me draw it this way vertically. Okay, and again, consider the height function. So in this case, I'll have 4 critical points. The minimum, let me call it small m. The maximum, we call it capital M. And we'll have 2 critical points here, P and Q. Okay, so here close to the minimum, basically this function locally is given by the same expression here as F close to the minimum. And to the maximum is the same expression as here. So let me just say what happens to P, close to P and Q, and close to Q. So close to P, F is given by F of P. And then I'll have, this will be plus x1 squared minus x2 squared. And close to Q, F is of the form F of Q minus x1 squared plus x2 squared. So we have this function with 2 critical points on the sphere, this function with 4 critical points on the torus. You may ask if we can we find a Morse function with 4 critical points, for instance, on the sphere. So we can do that, but instead of saying explicitly what the function is on S2 thought this way, what we do is we deform the sphere in such a way that the height function has 4 critical points. So now think of the sphere. I'm sorry, but I'll do it here so that the examples will fit on this board. Think of the sphere like this. So this is, I'm sure you can all see that this is the deformed sphere, smoothly deformed sphere. If I think of the height function on this sphere, it has 4 critical points, this minimum here, this absolute maximum here, and these 2 points here, let me call it this one P and this one Q. Okay? So close to this maximum, it has this expression. Close to this minimum, it has this expression. So let me just say what happens close to P and close to Q. So locally, close to P, F is given by F of P. This is, in fact, a local maximum. So this is just minus x1 squared minus x2 squared. And close to Q, F is of the form F of Q plus x1 squared, no, minus x1 squared plus x2 squared. Hopefully I'm not off by signs, but I think this is it. Okay, so this I here that gives me the number of minus signs that appear here is called the Morse index of the critical point P. So let me define down here, definition. The Morse index of P is equal to this I that shows up here, okay, from the Morse lemma. Small again, sorry, Morse lemma. So let me go back to that picture. So here for the North Pole, so the maximum, I have 2 negative signs here, so this has index 2. Here I have no minus sign, so this has index 0. Here, again, this minimum will have index 0. The maximum will have index 2. Here I have 1 negative sign. Here I have also 1 negative sign. So these 2 have index 1. Here, this minimum has index 0. This maximum has index 2. So P is a local maximum. Have 2 negative signs here. This has index 2. And this here has 1 negative sign, so this has index 1. Okay? Okay. This index, sometimes I just denote it by int P. It's the Morse index. Notation, int P. Okay, so now I need to tell you about the gradient. Okay, I'll erase this. To talk about the gradient, I need a metric. So let's assume I have a Riemannian metric on M. So M is endowed with a Riemannian metric. And this way I can define the gradient of f at x as the usual way, right? At p, sorry. the thing is, so here I'm looking into the gradient vector field. There are, so here in Morse theory, we can actually work with vector fields which are not exactly the gradients of the function, but are something similar, okay? And these are called the pseudo-gradient fields. And the idea is it behaves, I'll explain what it means, behaves like, in this case we want to look at the negative gradient, so let me put here negative gradient of f. And by behaves, I mean the following. So let me just make a remark first. So if you put here you look into the derivative, you put here the gradient, this will be greater or equal than 0. So if I put here minus the gradient, this will be less or equal than 0. So a pseudo-gradient field in particular needs to satisfy that this is less or equal than 0, okay? And close to each critical point, it is in fact this vector field. So this is what I mean by behaves by the negative gradient. Okay, so to this gradient, sorry. So to this pseudo-gradient field, or we can think of the flow associated to this pseudo-gradient field. So flow of the, I'll abbreviate this sometimes as pseudo-gradient field, okay? The pseudo-gradient field. And we can define, probably you've seen this, the unstable manifold at a critical point P, which is just the set of points x and m, such that the limit when s goes to minus infinity of phi s of x is equal to p, and the stable manifold x and m, such that the limit, this will be when s goes to plus infinity, this is minus infinity, this is plus infinity of phi s of x is equal to p. These are in fact manifolds, okay? The dimension of the unstable manifold is equal to the codimension of the stable manifold, and this is in fact equal to the index, the Morse index of the critical point P. And we'll say that this pseudo-gradient field satisfies the Smale condition. Let me see what the Smale condition is. So a pseudo-gradient field satisfies the Smale condition here, if these two, so all stable and unstable manifolds intersect transversely. Yes? What definition? Pseudo-gradient field. If you plot it here, it's less or equal than 0, and close to each critical point is in fact this. Okay. So again, if all stable satisfy, so this field satisfies the Smale condition if for all stable and unstable manifolds intersect transversely. Well, let me write this. So for all P and Q critical points of F, the unstable manifold intersects transversely the stable manifold. So intersect transversely means you take the points in the intersection, right, and you span the tangent spaces, and you see if it gives you the the whole tangent space of the manifold, if it does intersect transversely. So in this case, if you have this transversal intersection, then you know that this intersection here is a manifold. Okay, I'll call it MPQ. And in fact, you can check, or one can check, that the dimension of this manifold MPQ is equal to the index of P, the Morse index of P minus the Morse index of Q. Let me just go back to those examples. And let me just say the following. So let's look at the stable and the unstable manifolds here on the sphere. So if I look to the unstable manifold of the North Pole, it is basically given by all points on the sphere except the South Pole. So each point I take here on the sphere, okay, I can think of these. I know that in infinite time going backwards, I'll reach the North Pole. Okay, and all points satisfy this condition except the South Pole because I'm there. I mean, I cannot leave the point. What about the stable condition of the South Pole? Well, it's the set of all points on S2 on the sphere except the North Pole. Okay, so each point you take in infinite time, forward infinite time, or infinite forward time, you'll reach the South Pole. So when you do the intersection of these two, you'll get the sphere minus the two poles, the North Pole and South Pole. And when you take the tangent space at each one of these points, the sum will actually span the tangent space of the manifold. And the same happens to the stable of the North, same in the sense they intersect transversely because they won't even intersect, so they intersect transversely. Let me just point out that in this case, the Smale condition does not hold. So here, if you look to the unstable manifold of P, okay, it is basically given by two trajectories, the points in two trajectories connecting P to Q. These two trajectories here, let me see if I can, these two, right here, going downwards. Okay, and the stable manifold of Q is basically given by the same two trajectories connecting P to Q. So when you do the intersection, you get a one-dimensional thing, so it won't span the whole tangent space of the torus on each of these points. So here the Smale condition is not set. Well, I'm looking, these lines that I'm drawing here are the anti-gradient flow lines. It does not mean I cannot find a pseudo-gradient field here that satisfies the Smale condition. Okay. Just wanted to give you an example where it is not satisfied. Okay, so again, if we have the Smale condition, then this is a manifold, okay, with this dimension. And there's an action of R on this space by translation along the flow lines. So to MPQ. So for each S in R and X in this space, we look into phi S of X. This is a free action. So when I consider M the quotient of this manifold by R, I get in fact a manifold, which I'll denote by LPQ. And the dimension of this manifold is this difference of indices minus 1. So the index of P minus the index of Q minus 1. So this space here, see what happens here in one of these trajectories. When I quotient by the action, it just means that this whole trajectory is one point here in this space. Right? So points here are just trajectories. I should think of this as the space of trajectories. Sorry. Space of trajectories connecting P to Q. Okay, so see, let me point out that in order to define this space, I actually needed this transversality condition. And for this to make sense, I need the index of P to be strictly greater than the index of Q. Okay. So now we can define the Morse complex. To define the Morse complex, we'll consider vector spaces, which I'll denote by CK. So this is a vector space. I'll think of it over Z2. The important part here is that this is a field, okay? Well, it's more than that, we'll see. A vector space over Z2 generated by critical points of F of index, Morse index, okay, of Morse index K. So the vectors in here, the elements in here are formal sums of critical points P of index K, crit F K, here means the index is K, and the coefficient, here I'll denote it by AP, and this AP lives in Z2. So elements in here, I'll see them as formal sums of this form. So now I now need to define the differential. So the differential goes from CK to CK minus 1. And I'll say what it does to one of the generators of this vector field, of this vector space, sorry. So delta K of P needs to be an element in here. So it will be a formal sum of critical points of index K minus 1. And the coefficient, I'll call it N of PQ. And the idea is that it counts the trajectories that connect P to Q. Okay? So this NPQ, it counts the trajectories connecting P to Q. But it counts mod 2. So this is in fact in Z2. Okay, so how do we do this of counting these trajectories? So we have this space, LPQ, which is the space of trajectories connecting P to Q. And here, P has index K, and Q has index K minus 1. So the difference of the indices is 1. So this space has dimension 0. So here, in fact, this number here is the number of elements in LPQ mod 2. Okay? Okay, so we have this map, and now to define the homology, I need to guarantee that this dk plus 1, is it the other way? dk plus 1 is actually equal to 0. Okay, so let me give you the idea here. So what is this? What does this composition do to a point, critical point P? So this point P is now a critical point of index k plus 1. And when you do the composition, you'll get an element in ck minus 1. So here you go from ck plus 1 to ck, and here you go from ck to ck minus 1. So you'll get a formal sum. You'll get a sum of critical points of index k minus 1. Actually, let me call them R. And the coefficient here is the sum of n pq and q, oh, this is small, sorry, n pq times n qr, where q runs over the critical points of index k. So here I'm counting trajectories from p to q. Here I'm counting trajectories from q to r. Okay, no multiplying that. So in order to prove that this is 0, it suffices to show that this sum here, n of pq times n of qr, with q in the critical points of index k, this is 0 for all p and r. So p of index k plus 1 and r of index k minus 1. Okay, so let me draw a picture of an example to eventually convince you that this is 0. So we have our point, critical point P here. It has index k plus 1. We have this critical point R here, which has index k minus 1. Okay. And the space LPR, so the difference between these two indices is 2. So this manifold has dimension 1. Okay. And this manifold, it's the space of trajectories connecting P to R. Okay. It's a one-dimensional open manifold. In this case, let me sketch it here as an open interval like this. Okay. Now, see, what I'm counting here, what we are counting here is let me write it up here. What we are counting here is the number of elements of, so this NPQ is the number of trajectories connecting P to Q, right? So the number of elements in here. And this one is counting the elements on NQR, on LQR, sorry. Okay, so this sum here is counting the elements of this disjoint union of these spaces where Q is running over the critical points with index K. So let's look into this space here. So again, LPQ is the space of trajectories connecting P to Q, where Q is a critical point of intermediate index here between K plus 1 and K. Okay, so let me, in this picture, I'll just have a Q1 and a Q2, and they both have index K. So in this space here, I'm looking into the trajectories that go from P to Q, and to Q1 in that example, and here from Q1 to R. And here, from P to Q2 and from Q2 to R. So see, what happens to this LPQ1 times LQ1R? So this is my LPR. This product here, these two, this has index k plus 1, this has index k. The difference is 1, so this is a zero-dimensional space. This is also zero-dimensional space. So here in this picture, I'll draw it just here as this point. And for Q2, I'll have L of P Q2 times L of Q2R, which is also zero-dimensional, and I'll denote it here by this point. The thing is, we can consider the union of these three things and endow this union with a suitable topology so that I can think of this union as just a closed interval. Okay? And I won't go into detail, this is just the idea. Okay? So let me just say the union, I can think of it as this closed interval, and we'll denote it by LPR here with a bar. I apologize for this mess in the picture. Okay. So what happens is, yes?
It needs to prove this, you need the compactness of the trajectory.
Yeah, so I wanted to point this out. I won't go into into the details, but this is actually a point I want to focus, is that this is considered the compactification of this space. So this is a one-dimensional compact manifold whose boundary is given exactly by these spaces here, which are called actually the broken trajectories. So this is called a broken trajectory between P and R. So of course there's a lot to say here.
You're just counting the number of ends of in this case, the space, model space is one dimensional. The trajectory space.
Mm-hmm.
So when you take the boundary, you're just counting the number of ends.
Exactly. And since it's a...
Because it's an interval, so it's a given number.
Exactly. So you know it's a one-dimensional manifold, compact manifold, so the endpoints, so you know it's the union either of spheres or closed intervals, so you know that when you count these points here, you'll get mod 2, you'll get 0. Here, sorry, 0. Right? So this is how I should have, at least the idea should convince you that this is 0. I'm counting endpoints of one-dimensional compact manifolds, and so mod 2, this is 0, because they're all even. Okay? So let me just emphasize three things we have used here to construct this complex. So one thing we needed was transversality, given here by the Smale condition, just in order to define the space of trajectories LPQ. We needed the compactness of that space LPQ, the bar. And in fact, we needed to understand the boundary structure of that manifold. Let me write it here, boundary, in order to prove that that composition was 0. Okay. So given, and these are three main steps you usually go through when you want to construct a Morse type homology. Okay, so just to let me finish defining the Morse homology. This is M of Z2. This is given by the kernel of delta K over the image of delta K plus 1. Of course, there's one more thing here to check. which is that this does not depend on the Morse function we took, and it does not depend on the pseudo gradient field we took to make this construction. So let me state this as a theorem. So given two Morse functions, f0 and f1 on M, and two pseudo gradient fields, so x0 is a pseudo gradient field of f0, and x1 is a pseudo gradient field of f1. Then there exists a morphism on the complexes that induces an isomorphism on the, sorry, continue here. There exists phi star morphism from the complex constructed using f0 and x0, and the complex using f1, sorry. What I want to say is here the differential using the pseudo gradient field x0, and here I mean the differential using the pseudo gradient field x1. So there exists a morphism which induces an isomorphism on the homology. So the Morse homology. Okay. And as a consequence, let me call it a corollary of this, we can in fact check that the number of critical points of a function f mod 2 is actually equal to the dimension of the Morse homology of S. So let me actually go through the idea of the proof of this corollary. So to count the number of critical points of a function f, all we have to do is to sum basically the generators of each ck. So this will be the sum of the dimensions of each vector space. Ck, k running over 0 to n plus 1. Let me draw the complex actually. So Cn minus 1, Ck minus 1, C0, 0, 0. This is delta k, so this is delta n, this is delta n plus 1. So this runs from, sorry, k equal to 0 to k equal to n. Okay. Now by the rank nullity theorem, I know that this dimension is equal to the dimension of the kernel of the differential, delta k, plus the dimension of the image of delta k. K here running from 0 to n plus 1. Okay? And then, just by rearranging the indices, if you want, this is the same as the sum from, with k running from 0 to n, I think, I'll check in a moment, of the dimension of kernel of the delta k. So this is this delta k. Now I'm not considering delta n plus 1. The kernel is 0, so it's okay if I ignore it. Plus, and now let me write the dimension of the image of delta k plus 1. So here when I do k equal to 0, I'll get here delta 1. So I'm ignoring here the delta 0 here, but the image of delta 0, just this one, d0 is 0, so it's okay to ignore it. So I got that the number of critical points is given by this sum, okay? But mod 2, this is the same, we continue here. This is the same as the sum of the dimension of the kernel of delta k minus the dimension of the image of delta k plus 1. Mod 2. But this is exactly the dimension of the Morse homology. Okay, so this is the sum of the dimension. The Morse homology of M over Z2. So this k is running from 0 to n, from 0 to n. So mod 2, this number is equal to that dimension. And using a very similar computation, we can actually prove that the number of critical points of F is greater or equal than the sum of the dimensions of the Morse homology M over Z2, with k running from 0 to n. And this is called Morse inequality. Okay. So the proof ended here. Okay. So let me just check. Come on. Okay. Okay. So before I do a short break, let me try to summarize what we've done here. So for the Morse homology, okay. So we started with a manifold, and we started with a function f defined on this manifold. We started with the Morse function, so all its critical points are non-degenerate, and we constructed a complex where these vector spaces are the vector spaces generated by the critical points, each one with index k, this Morse index that came from in this case, from the Morse lemma. And the differential was defined using these trajectories connecting the critical points of this function. And again, let me emphasize these three things here that we needed to actually prove that this will define a homology. So the transversality, which we need to define the space L of trajectories, the compactness, and here boundary, to make sure that the differential is actually different composition here. Will satisfy this property, so we can define the homology, the Morse homology. And we have the invariance of the homology, and with this invariance, we can actually prove this Morse inequality. Okay? So now after the break, what I'll do is tell you about Hamiltonian Floer homology, but you should have these steps in mind when we do that. Okay. I don't know if there are any questions. If not now, later is okay also. Feel free to ask them.
We can also ask questions during the break.
Yeah, perfect.
Private if you prefer.
Okay, so for now, it's all.
So just before we leave, I was asked to organize some